No one knows what x to a negative power means? It means it's 1 over. And what happens as soon as you put a variable in the denominator? As soon as you put a variable in the denominator, you run the risk of having an undefined value. And once you have an undefined value, can you have a nice, smooth, flowing curve? No, it'll be broken wherever the undefined is. So, if you have a negative exponent, so the problem in the homework was, tell me the degree and leading coefficient of this thing. Okay, you can't, because it's not a polynomial. That is not a polynomial because of this. Okay? All right, so that's the one thing I noticed. I can't remember anything else I noticed, so you ask me. Who has a question about something from one of the homeworks that I turned out?
1.6, number 5.
1.6, number 5. Number 5. Okay, well, this says use a calculator. So you are not at this point expected to be able to graph this. Now, we're getting there in this unit, 1, 7, 1, 8, 1, 9, 1, 10. We're going to get there, but right now, you're not expected to be able to graph that thing on your own. So you put it in your calculator, and what shape did you get? Because we're finding the limits. We want to know what happens as we go off the page or off the screen. What's happening? So let's graph it and see what we get. What do we got? 3x plus 1 divided by okay. Are you looking at it with me? I'm seeing something that looks sort of like this and sort of like this. Are you seeing something that looks like that? That's what you should be seeing. Okay. Now, as I'm going off the page this way, so this would be heading toward negative infinity, does it look like this thing is kind of flattening off? Yeah. And similarly, going this way, it looks like it's flattening. Okay, now it's not becoming horizontal, but it's getting closer to horizontal because there's an asymptote running right through here. It's straight, but you can't see the asymptote, but you can figure it out. I want you to think about this fraction. What happens when x gets really, really big? When x gets really, really big, how significant is that plus 1? Not. So ignore it. Basically then, you have 3 zillion trillions over negative 2 zillion trillions. What is the equation of this horizontal line that our curve is approaching? Negative 3 halves. So your horizontal asymptote is negative 3 halves. That's the limit. That's where this is going. It's getting closer and closer to negative 3 halves. Okay? Now, on this side, it's getting closer and closer to negative 3 halves from the top of the picture. Remember that notation we talked about? And on this side, it's getting closer from the bottom. Both sides are approaching negative 3 halves. But one side is coming in from the top and the other side's coming in from the bottom. Okay? Good. Everybody good with that? Okay. Now, what about the second one? What does it look like when I graph it? 3x squared.
Bless you.
Okay, now this one looks a little bit funky. This one looks like, oh, let me write the problem down. Something like this, and then over here, something like this, maybe? What's happening to this picture as we head off the page to the left? What's happening to the curve as we go off to the left? Where's it going? Down. That's negative infinity. Now, somebody, and I don't know where this came from, but somebody gave me the equation of the slant asymptote, and that, it is approaching that line, but it's actually heading to negative infinity, because that's where the line is going as x approaches negative infinity. And what about on the other side? Where's this one going? Positive. Okay, Anna?
Yeah.
All right, let's do one more homework question. Anybody else have one? From anything? Josie?
On 1.5, for number 4, where you're using a calculator, how do you find imaginary zeros?
We aren't, and we don't need to in this case, because, Josie, if you look at that picture, I have real zeros. Actually, for number 5, you said, or number 4?
Number 4.
For number 4? Yeah. For number 4, no. Okay, what is the degree of the polynomial in problem number 4? Okay, so what does that mean? That means there's 3 roots, right? They tell me that one of them is 2 plus 3i, which automatically means that another one is 2 minus 3i. Now that's 2, you said there's 3, right? Is the third one gonna be real or imaginary? Gotta be real. Why can't the third one be imaginary? Because there isn't a fourth one, right? And they come in pairs. So all you need to do, Josie, is draw a picture of that curve, and it's gonna cross the x-axis someplace. And according to my work, it crossed at 4. So here are your roots. You are not finding any imaginary ones. They tell you one, and you know the other one automatically. All right, Kennedy, what was your question?
1.59a.
Determine if it's even, odd, or neither. So we have a technique for doing that based on what we know even and odd means, okay? So even means that if you plug in a negative, you get the same thing as if you plug in a positive. That's what even means, okay? So if I'm checking for evenness, I already know that g of x, f of x, g of x, is 2x cubed minus x plus 1, okay? Now I'm gonna do this side. I'm gonna see what this is. So I'll use f, it's really g. F of negative x would be 2 times negative x cubed minus negative x plus 1. So simplifying, that's negative 2x cubed plus x plus 1. Does that match the original? No. And if I'm going to be even, it has to match, okay? So it's not even, because f of negative x does not equal f of x. If it's even, when you plug in your negative, you're gonna get the original problem back again. Okay, but I can tell right now it's not odd either, because what happens in an odd? Every sign changes, right? So that would have to be negative f of x, which would be negative 2x squared plus x minus 1. So since neither one of these were true, Kennedy, neither one was true. It's a neither. That's a neither. Okay? Some of you, most of you, can look at the equation and say, oh, that's not gonna be either, but you gotta show some work, guys. Okay, just being smart is never good enough, you gotta show some work. Okay, perfect. All right, let's get our review sheet back out and let's see if we can get that done. Because we're gonna have a quiz tomorrow, so we definitely wanna get this done. Okay, so I think we're ready for number 13, is that right? All right, so we got a couple of tables here, 13, 14. And we just have to figure out which, it's multiple choice, which one's true. All right, so I'm getting stuff copied down. Why don't you go ahead with your partner and start working on 13 and 14, seeing if you can figure out what you're supposed to be doing.
Okay, I thought that was 14.
Is the quiz gonna be the same format as the last one? Like,
Yes.
book size?
There'll be more free response on this one than there was on the last one. I tried to put some multiple choice on here, they're so hard to write. Okay, all right, so what do you come up with? Have you got a plan for 13? What do you think? I wasn't sure, I just started doing average, or finding the differences here. And since these are equal length intervals, these numbers aren't the average rate of change, but they're the average rate of change is gonna be the same, it's gonna be 18, or not the same, but 18 over 3 would be the rate of change here, 36 over 3, 54 over 3, 72 over 3. So the ratios are staying the same. So, tell me what you came up with. What did you decide? Which answer did you pick? You guys didn't even pick an answer. Oh, you did? Okay, it's gotta be quadratic. Would everybody agree?
Yes.
Okay. How do we know it's quadratic?
Second degree.
Well, one way is the second differences are the same, but that isn't an option for a choice. So what am I gonna pick for my choice? Which one? The rate of change over consecutive equal length input value intervals is constant. This is the rate of change. Is it constant? Actually, that's not the rate of change. The rate of change would be G's over 3. Are these constant? Now wait, are these numbers all the same? That's what constant means. Are they all the same? No. If they were all the same, we wouldn't be quadratic, we would be linear. Okay. The rate of change over consecutive equal length input value intervals is linear. Look at these numbers, 6, 18, or no, not 18, 6, 12, 18, 24. This is a linear relationship. What's happening? Isn't it going up by 6? That's a linear relationship. It's changing by the same amount. So the answer is D. Constant means these numbers are exactly the same, and they are not. But they're going up by a constant amount. That's a linear relationship. Okay, what'd you decide about 14? Do you have any decisions about 14? I did the same thing, I don't know if I wanna do that or not, but what did you come up with there? Which one? D, everybody said D? The graph of H could be concave down because the average rates of change over consecutive equal length input values are decreasing. Here are the actual rates of change. Are these numbers decreasing? And if the rate of change is decreasing, then we know our curve is concave down. Perfect. You guys are amazing. All right, next one. Which is true? Same kind of question. Which is true? Increasing at an increasing rate, decreasing at a decreasing rate, increasing. What do you think? C. Increasing at a decreasing rate. How do we know it's a decreasing rate? Concave down. Perfect. You guys are awesome. All right, 16. Global max. Where is it? The global max, if there is one. Where is it? Just give me the point. Point B. Notice that A does not have an arrow, so we're not shooting up. Everything okay?
Yeah.
All right. Local minimum. Do I have any local minimums? B. B is a local minimum. Relative maximum. Which A and D, aren't they both relative maximums? The highest point within that little area. Absolute minimum, I'm trying to use all my words. Absolute minimum is non-existent. Why not? The arrow, see it? Going down. Where is f of x greater than 0? Between A and G? And between F and E? Now, if we were using actual numbers, you would be using your open interval notation because it's just greater than 0, right? All right, where am I less than or equal to 0? G to F, and then e to infinity, and those would be bracketed.
If we were using interval notation for E, would there be a bracket on A since it's above?
Uh-huh, yep, yep. Do I have any points of inflection? Okay, so let's pause. What are points of inflection? What do I look for on the graph? Where concavity changes. So think about tracing the curve, or actually trace the curve. When it starts, would you agree A to G appears to be concave down? But then what about G to F? Actually, maybe even G to C, right? Looks like it's concave up. So where did I change concavity? It looks like one point of inflection is G. And then I think you could argue either way. Would you agree there's another one at either F or C?
Yeah.
One of those two?
Yeah,
And then I think that's it, right? All right, where am I concave up? Between what letters am I concave up? G to F or G to C, depending on how you're looking at it. That's it. And where am I concave down? A to G, and then F to infinity or C to infinity, depending on where you put that point of inflection. Increasing. There's only one part of the graph that's increasing, and that's from B to D. Decreasing would be A to B and D to infinity. Decreasing and concave up. Yeah. I think Patrick's right. I think G to B is the only part of the picture that's decreasing and concave up. Would you agree with that? And decreasing and concave down. A to G and D to infinity. All right, so now in number 17, this is review from the last quiz. Number 17, we have functions written as a rule, so we have this guy, and a piecewise function, so we have this one. And then we have the picture, and then we have a table. So, I'm not gonna draw the picture, but here's the table. All right, so now we have to find the average rate of change on the given interval. So, from -5 to 5, how do we find the average rate of change? Oh my gosh, if we haven't learned anything, we need to have learned this. From -5 to 5, f of 5 minus f of -5 over 5 minus -5, right? So f of b minus f of a over b minus a. So here's f, that's the function we're looking at. You gotta pay attention to the letters, so we're doing f. So what's f of 5? Oh, let's use a calculator, this is going to be big. F of 5. I got 366, but check my math, would you, 366? And then -5. I got -364. Did you get 73? Did did I do okay with that? Okay, all right, G. Now we're going from -3 to 3. So that's gonna be G of 3 minus G of -3 over 3 minus -3. This is gonna be our average rate of change. So look at your G function. First thing we gotta find is G of 3. Where does G of 3 fit in our piecewise function? Top row or second row? Second row, bigger than 2. So I'm gonna put in 3 here, and I'm gonna get 11. Now where does -3 fit in all this? Top row. So I'm gonna plug in -3, and what is that? 14. Oh, how's my arithmetic? I got -1/2. Okay, C can't be. Look at that interval. What in the heck was I doing? Make that 5 negative. In letter C, it should be, the interval should be -5 to 3. So let's do h of 3 minus h of -5 over 3 minus -5. Here we go. Look at your picture. What's h of 3? -2. Perfect. What's h of -5? 3. So did you come up with -5/8? So easy. And then K, find the -2 to 5 on this one. So that's going to be K of 5 minus K of -2 over 5 minus -2. All right, so K of 5 is 14. This is the easiest one of all. K of -2 is 8. I got 6/7. We just talked about. It was in our homework. We just reviewed it. How are we going to prove that P of X minus Q of X is not even? Maybe we should start by figuring out what P of X minus Q of X is. So 3x minus 5 minus x cubed plus x squared plus 7x. So it looks like the function in question, which I'll call d of x, I'll let d of x be the difference here. So the function in question is -x cubed minus x squared minus 4x minus 5. Did I get everything? Now I have to prove that this is not even. You all know it's not even. But how are we going to prove it? We're going to find d of -x, right? And what should happen when we find d of -x? It should match this, if it's even. So here we go. First of all, is this okay? I didn't make any mistakes here, did I, before I go on? All right. Xander, you just nod your head. You're half asleep over there. Are you paying attention? Okay. All right, so -x cubed minus -x squared minus 4 times -x minus 5. So that's going to be positive x cubed, negative x squared, positive 4x minus 5. So how do what do I say? My job was to prove, what am I gonna say? Since d of x does not equal d of negative x, d of x is not even. How does that sound to you? Isn't even this right here equal to each other? Since they didn't turn out equal, then the function can't be even. Last one. Oh my, what's going on here? Part of the graph is shown. I know that m of x is an odd function. So I need to use whatever I've got here and figure out, that's only part of the graph, that isn't all of it, that's part of it. I have to find m of 5. All right, let's think about this for a minute. What does it mean to be odd? It means m of 5 will be negative m of negative 5. So I want you to think about that for a second. Odd means that if you put in a negative, you get out a negative, correct? That's what odd means. Okay, what do I get at negative 5? What is my function value at negative 5? 4? So if m of negative 5 is 4, then m of positive 5 is going to have to be negative 4. If the functions are odd. Now, if this were even, this is odd. If it were even, what would m of negative 5 be? Or excuse me, what would m of 5 be? M of 5 would be the same thing if it were even. If it were even. All right, how about m of negative 1? I don't know, what's m of 1? Negative 1.5. So m of 1 is negative 1.5. So what's m of negative 1 going to be? Positive 1.5. If you are odd, changing the sign on input changes the sign on output. If you are even, changing the sign on input has no impact on the output. The output stays the same. Okay? Julia?
When we were finding m of 5, why did you write m of 5 is equal to negative m of negative 5?
Well, I was thinking it through in my head. The easiest thing to do is find m of negative 5 on the picture. And then whatever that is, change the sign of it. That's what this means. Change the sign of the negative 5 one.
Negative of a negative. Okay.
If you change the sign on your input, Julia, you're going to change the sign on the output. That's what odd means. Okay? So when I looked at my picture and it said m of negative 5 was 4, then I automatically know if I make that a positive 5, this is going to a negative 4. That's what odd means. Ellen?
For number 18, are we not allowed to prove it from like the degree?
No.
Okay.
No. Because not everything with an even degree is going to be even, and not everything with an odd degree is going to be odd.
Okay.
Because there's other things that can be thrown in there. All right, let's put that away. Quiz tomorrow. Hopefully I will get it written. It's forever we write these things. Now let's get our notes out and spend a few moments with 1.7. Oscar. ask about the quiz, the format, and it will be part true response and part multiple choice, just like before. There will be more free response on this one than there was before, because there'll still be some multiple choice. Okay. A rational function is simply the quotient of two polynomial functions. That's it. So all the things that we've been drawing and talking about, put one on top of the other, and you've got a rational function. Clearly, anytime that you have a denominator, you have to worry about things being undefined. So that's going to be a big part of what we talk about. Okay. Let's hold off on all that formality there in the box, and let's just look at a couple of problems here and see if we can figure some of this out on our own. And then we can go back and talk about that box. Determine if the following rational functions have a horizontal asymptote, slant asymptote, or neither. If the function has a horizontal asymptote, write the equation of the asymptote. Okay, so what we're talking about is end behavior. We're wondering what happens as x gets really, really big. So think about what we talked about a little bit earlier, actually, with the homework problem. If x is getting really, really big, where is the power in the, where's the control in the numerator? Isn't it this term right here?
Yeah.
If x is like a trillion, this is a trillion squared, that's huge, right? And in the denominator, isn't it right here? So as x is getting really big, then this is the only part of the problem that really matters. It's the most important part. This one has a horizontal asymptote. What is that horizontal asymptote? 3/5. Horizontal asymptotes are a form of end behavior asymptote. So you're asking yourself what happens as x gets really, really big. Now, let's look at B. Take a look at this and tell me what you think the horizontal asymptote might be. This has a horizontal asymptote. What do you think it might be?
2.
Good guess. No. I get it though. I totally get it where that came from, but no. 0. Who said that? Why, Drew?
Because the bottom has a higher power, so it'd be like 1 over.
Exactly. Remember, we're talking about letting x go to infinity. So if x is like a trillion, this is 2 trillion, that's big, but this is a trillion squared, which is a whole lot bigger. So the way when we do this in CP and academic, and we're not quite so intuitive, I always say, look, over here, you looked at the x squareds, right? So I'm gonna do the same thing here. I'm gonna look at the x squareds. That's where the power is. But I don't have one on the top. So when I compare my x squareds, it's 0 over 1, which is 0. Your horizontal asymptote is 0. Now, I don't know if you're listening to Drew or not, but he said the power on the bottom is bigger. When that happens, your asymptote is always going to be 0, because the fraction is always going to get smaller if the denominator power is bigger. Great. Now, what happens with C? What's happening here?
2/5.
Again, it's a great guess. It's It's not right, but I get it, totally, I understand that. What did I compare here? X squares?
Yeah.
What did I compare here? I had to fudge it a little bit, but I compared x squared. Guess what I'm gonna compare here? X squared. How many do I have in the bottom? Uh-oh, what happens when I compare those x squareds? There is no horizontal asymptote. Now be careful. There's no horizontal asymptote. Remember that one from the homework, and I don't remember the shape exactly, but you know, something like this. I don't remember exactly what it looked like, but it was shooting out like this. That is what would happen here. You would have what we call a slant asymptote. We're gonna figure out how to find that. It's real easy. We're gonna learn how to find that slant asymptote. And the picture is continuing to rise and fall along that horizontal, or that slant asymptote. But the point of this exercise is there's no horizontal, because you can't have 2 over 0. All right, tell me about D. What's the horizontal asymptote in D? 1/2. Mrs. Ford, there's no x squared. You're right. So I don't look at the x squareds in this problem. I look at the x's. Whatever power is the biggest, that's what I look at. So it's 4 over 8 or 1/2. Y equals 1/2. Tell me about E. Y equals 0. Again, it's Drew's rule. The denominator is bigger. If the denominator power is bigger, it's going to be y equals 0. And how about F? Y equals 0. That's your horizontal asymptote. Y equals 0. All right, example 2. We'll get through a few of these and then we'll call it quits, because you're all exhausted for some reason. Okay. 2A. We have this big, giant rational function, and you have to describe its end behavior. Right, limit statements. So the limit as x approaches negative infinity, and the limit as x approaches positive infinity. This is how we always express our limits. Okay? Tell me what you think. Think about what's happening. Does this thing have a horizontal asymptote? Yeah. That will be the limit. If it has a horizontal asymptote, that will be the limit. So what is its horizontal asymptote? 1/3. Now, would you guess that if we graphed this, so here's 1/3, would you guess that on one side of the picture, it's coming in from the top, and on the other side from the bottom? Would that make sense to you based on just the very few that we've sketched already? How do you think we can figure that out? Well, let's graph it on our calculators. This will be the last thing we do. Let's graph it on your calculator and see if you can figure it out from the picture. And we got to talk about how we got to be able to figure this out without our calculator. Well, let's see if we can figure it out with the calculator first. picture. I couldn't tell from my picture, it's so screwy, so I pressed my trace button and just arrowed through it to watch my Y coordinates. Do you know what I'm talking about? Press trace, and then the cursor comes up and just move it and watch those Ys. I was wrong. What happens in this one? No, those are horizontal asymptotes, but they're both sides are coming in from the top, aren't they? Both sides are coming in from the top. That is actually the right picture. Maybe I don't have the right picture, because that sure looks like the right equation. Did you all get one top and one bottom? Yeah. I can't figure out my mistake. Okay, well then my guess was right. So, I got the wrong picture. Xander, what happens on this side? Negative, what happens on the left?
It goes
Coming in from the top?
Yeah, from the top.
And then this one was the bottom. Alright, I gotta figure out that I typed wrong, because I think I typed it right, but I'll have to figure that out. And figure out why that's wrong. But anyway, one more and then we'll, stop. How about B? Let's not, before we graph it, can you tell me what the horizontal asymptote's gonna be? Yep. So both of these are coming in closer to 0. And 0 is a little easier number to deal with because you're just talking about whether it's positive or negative, right? Okay, we'll come up with a plan here. Go ahead and sketch it if you want. I'm scared to sketch it. I don't know what I did wrong. Anybody got something yet? On the left, it looks like it's coming in from the bottom and the right's coming in from the top.
Yeah.
Okay, all right, we'll stop there. None of that stuff's on your quiz, just what's on the review. Make sure you learn. We'll go back and redo the review. And we will pick up here.
So it's 170 Thursday.
No, we're not done. We have quite a bit to talk about. We'll finish it. Yeah, no homework yet. We have a class session. Okay, everyone, hit your phones, but sit back down.